So the first thing we're going to do is we're going to start talking about section 2.3, which is about continuity. What I'm going to start with is just kind of going through some of the vocabulary that we were going to use to talk about these graphs. And then we will look at some examples where we have to actually give some information about the graph using this vocabulary. So intuitively, which means like just sort of it makes sense, we would say that a function is continuous if there are no holes and no asymptotes. The reason we would say this is because the word continuous literally means nice, smooth, and connected. And usually when a graph is not nice and smooth and connected, it is because the graph is going to have a hole or an asymptote somewhere. So if we look at this example, this is a graph that is continuous. I can trace the entire graph without lifting my pen. And if I can do that, it is continuous. So I can draw the whole graph without lifting my pen. Now let's take a look at a graph that is not continuous. So if you look at this example right here, this graph is not continuous because at this specific spot, the graph is broken. It's not connected. There's a hole on this end, there's also a hole on this end, and they jump from one to the other one. I could not draw this graph without lifting my pen because I could draw the first part and get to the hole, but then I would need to lift my pen to draw the second part of the graph. And when that happens, you know that you're not continuous. Now we say that when you're not continuous, the function has a discontinuity. So since not every function is continuous, we say that it has a discontinuity, which is literally discontinuity, at that specific x value. So we would say that this graph has a discontinuity at x equals whatever this number is. Since we're calling it x sub naught, we're going to just call it x sub naught. Now that means since there's only one spot where this graph is disconnected, we would say it's continuous everywhere else. So except for this one spot, everything else would be nice and smooth and connected. So we say that the function is continuous on an interval. What that means is that we cannot just list all of the x values where we are continuous, because if we tried to do that, there's no way to list all of these numbers. You would need to have like 0, 0.00001, 0.00002, 0.0003, and then there would be even more numbers because you'd have to add more zeros. So since it's impossible to just list them all, we say it's continuous on an interval, and we only say this if it is continuous at every point of the interval. So we would say that it's not continuous at this spot, which means if I asked you to look at an interval of the graph where this spot was included, you would say it's not continuous on that interval. So it has to be continuous everywhere on the interval in order to say it's continuous there. So if I said, where is this graph continuous? You would say from negative infinity to x sub naught. And I'm going to make both of those open brackets, which means I'm using a parentheses. The reason I'm using a parentheses is because it is not continuous at this endpoint, since it's an open circle. And we never get to use a closed brackets for infinity. Infinity cannot be contained. And it's also continuous from x sub naught to positive infinity. Again, I'm not including the x naught because that's an open circle. If either of these endpoints was a closed circle, then just that section of my answer would have a closed bracket, which is like a square bracket. So let's look at some examples where we have to use this definition. If it says find the points where the function is continuous and the places where the function is discontinuous. So let's start with continuous. In this graph, my function would be continuous in a lot of places. It's continuous for this entire section of the graph, but it stops and is broken at the -1. Then it's continuous for this entire section of the graph, but it's broken at the 0. Then it's continuous for this section of the graph, but it's broken at the 1. There's a hole there. And then it's continuous past the 1 from 1 to infinity. So if I were to list all of those intervals, here's what I would say. I would say from -infinity to -1, and I'm going to include the -1 because this is a closed circle. We are continuous. Then from -1 to 0, and I'm making both of those open because there's an open circle here and this just goes up, up, and away, so it's not going to touch the 0. Then from 0 to 1, I would be continuous, and I'm making both of those open because both ends of that interval are open circles. And then from 1 to infinity, and I'm making this one open because that is an open circle on the graph. If I were to say, where are you not continuous? So where do you have a discontinuity? Instead of listing intervals, I would list specific x values. So I would have a discontinuity at x equals -1, because that's the first place the graph is broken, at 0, because that's the next place the graph is broken, and at +1, because that's the next place the graph is broken. All right, we're going to save example 2 in case we need to talk about it tomorrow. And let's go ahead and try the problems on the next page. So in terms of limits, which is what this chapter is really about, how can we use limits to determine whether a function is continuous or not? So we can say that a function is continuous if these 3 things exist. If the limit as x approaches your whatever x value, I'm going to call it like c. If the limit as x approaches that number from the left of your function has to equal the limit as x approaches that number from the right of your function, which has to equal the function value. So this means when you slide from the left, when you slide from the right, and the actual point all have to agree in order for your function to be continuous. Now, if it's an endpoint, then instead of checking both the left side and the right side, you just check whichever side is actually connected to the graph. So for example, on this end of the function, I would only check the limit as x approaches a from the right, because that's the only side that actually has a graph connected to it. I can't check the limit from the left because there's no graph over there. So we need 3 things to be true. The limit from the left, the limit from the right, and the actual point need to all have the same answer in order to be considered continuous. And what that means is that there are only 4 situations where you have a discontinuity, and we give them special names. For example, here we would say this is what's called a jump discontinuity, because the graph literally jumps from one y value to a different y value, and they're not connected. Now, if I look back at what I need to know the limit from the left and the limit from the right are the same as the function value. This graph violates the fact that the limit from the left and the limit from the right are not the same. If I approach from the left, and if I approach from the right, the arrows do not point to the same place. So we would say that the error is that the limit as x approaches c from the left does not equal the limit as x approaches c from the right. Now, we would not say that it doesn't match the actual point because the left side does connect to the closed circle. So it does match the actual point on one of the sides. It's just that the two sides themselves are not the same. Now, if I look at this discontinuity, we call this one an infinite discontinuity. The reason we call it infinite is because it literally goes up to infinity. There's an asymptote there. If I try to think about which of these rules it violates, the limit from the left and the limit from the right are pointed in the same direction. They agree on infinity as the answer. What's the broken part here is that the actual y value doesn't exist because you can't touch that asymptote. There's no closed circle to connect to. So the error here would be that the limit as x approaches c from the left, which is equal to the limit as x approaches c from the right, does not equal f of c. So those two limits might agree, but they don't agree with the actual closed circle because there isn't a closed circle. Now, this function right here is what we call a removable discontinuity. Basically, a removable discontinuity is a hole without a jump. So this one jumps from one section of the graph to another section. This one, there's only one spot that has an issue. It's a hole without a jump. And what we have is a closed circle that is somewhere that is not in the hole. So it's not actually jumping from a section of a graph to a section of a graph. It's just one spot has a hole in it. Now the error here would be, let's see, the limit from the left and the limit from the right agree. They're pointed to the same spot. However, the closed circle is somewhere else. So the error here would be that the limit as x approaches c from the left, which agrees with the limit as x approaches c from the right of f of x, does not equal the function value. The limits agree, but the function value is in a different spot. Some students have trouble telling the difference between a jump and a removable discontinuity. They have different kinds of errors. Here, the limits do not agree. Here, the limits agree, they just don't match the function value. And the last kind of discontinuity is what's called an oscillating discontinuity. You only see these with trig graphs, and they don't come up very often. But basically what happens here is just like a trig function, you're going up, down, but you're going up, down so fast that the left side limit and the right side limit never agree. Basically, when I approach from the left and when I approach from the right, one of them is going to be at the top and one of them is going to be at the bottom, and they're going to switch. So you're never going to agree on where your limits are pointing. So the error here would be that the limit as x approaches c from the left does not equal the limit as x approaches c from the right. Okay, let's take a look at an example. So in this example, we're going to do a bunch of different things. We're going to find the discontinuities. That's part A. We're going to classify the discontinuities. That's part B. That means like say, is it a jump? Is it removable? Is it an infinite? We're going to use limits to explain why it's not continuous. And then the last thing is going to be to identify where it is actually continuous. Now I'm going to kind of group A, B, and C together because I think it's easy to answer these questions all at once, and I'll show you why. So let's group A, B, and C together. The first step in part A is just find the places where you're discontinuous. So if I slide from the left side of the graph to the right side of the graph, the first spot where I have a discontinuity is -3. There's a hole there. So I would say I am discontinuous at x equals -3. Because this is a hole, and it's not jumping from one section of the graph to the other one, we would call that a removable discontinuity. And we would say that the limit as x approaches -3 of f of x from the left is equal to the limit as x approaches -3 from the right, but it is not equal to f of -3. Oop, you can't really see what I wrote there. Sorry. Sometimes it's hard to tell what you guys can see and not without checking, so I apologize for that. So let's just take a second and process that. The limit from the left agrees with the limit from the right. It just doesn't agree with the function value, which is why we write it this way. Now you'll also notice that I didn't put c's here. Here we have specific numbers. We're talking about what happens at -3. So these limits should be -3 from the left and -3 from the right. Now if I keep sliding along the graph, the next spot where there's a discontinuity would be at x equals -1. This time the graph jumps from this section to this section. So this would be called a jump discontinuity. And if we wanted to use limits to explain that, the limit from the left and the limit from the right disagree this time. So we would say that the limit as x approaches -1 from the left does not equal the limit as x approaches -1 from the right. If I continue to move along this graph, the next place where there is a discontinuity would be at the +1. Here we have a jump and a third point, which is the actual function value down here. So here we would say x equals 1 has a discontinuity. Again, this would be a jump. And if I wanted to use limits to explain this, I would say the limit from the left and the limit from the right disagree, and they also don't equal the function value. So I would say the limit as x approaches 1 from the left does not equal the limit as x approaches 1 from the right, which does not equal f of 1. Now if I continue to slide along the graph, the last place where there's a discontinuity is actually the end point at +4. This would be a removable discontinuity because there's a hole in the graph and the closed circle is somewhere else. If this point was connected to more graph, then it would be a jump. So here we would say that this is a removable, I'm calling it a hole, I'm sorry, removable discontinuity. And if we wanted to use limits to explain this, because this is an endpoint, we're not going to talk about the left side limit and the right side limit because there is no right side limit. We're just going to talk about how the left side is not the same as the function value. So here we would say that the limit as x approaches 4 from the left is not equal to f of 4 because the closed circle is somewhere else. Okay, so the last part here is just to state the places where we are continuous. So unlike parts A, B, and C, we're trying to look now, instead of for the discontinuities, we're trying to look for where you are continuous. Well, I would be continuous everywhere in the graph until I get to -3. So I would say closed bracket -4, comma -3, and I would make that open because that's the first spot where I'm not continuous. Then I'm continuous until I get to -1. So I would say open parentheses -3, comma -1, open, because both of those have open circles. Then I would be continuous from, now I'm going to make this closed, because this is a closed endpoint of this section, from -1 to 1 and make 1 open. And then I would be continuous from 1 all the way to 4, and I would make 4 open. Now, some students wonder, should I put a stopping point at the 2? If it's not a place where the graph is discontinuous, you don't have to create a separate interval. So you could go -1 to 2, +1 to 2, and make 2 closed. And then you could also do closed from 2 to 4 and make 4 open. But it's just more work. It's 2 intervals. Sorry, you can't see what I wrote. It's 2 intervals to say the same thing as 1 interval. All right, we're going to go ahead and stop there. We've got a couple examples that we could try at the beginning of class tomorrow, and then you will have the rest of the class period to work on some practice problems and make sure you really understand this. Thank you so much for watching, and I will see you next time.